All right, let's dive into something that you're using literally every second you're on a computer, but you probably almost never think about. It's memory. We're going to peek behind the curtain and figure out what makes it so fast and, well, what makes it so slow. So you've got the latest and greatest processor, right? A multi-gigahertz monster that can just chew through calculations. But you still see that spinning wheel sometimes, don't you? Why does it feel like your computer just takes a pause before opening a big file or loading a new level in a game? Well, the answer lies in a fundamental traffic jam happening deep inside your machine. And that traffic jam, that's what we call the great speed gap. I love this analogy. Imagine your computer's processor, the CPU, is like a Formula One race car. It's just engineered for pure, blistering speed. But the main memory, where all the data actually lives, that's more like a heavy cargo truck. And it doesn't matter how fast that race car is, it can only go as fast as the truck lumbering along in front of it. And the scale of this gap is just staggering. A modern CPU can be humming along at nearly 4 gigahertz. But the main memory it has to constantly talk to might be running at less than half that speed. That's a huge mismatch from the get-go, and it creates the single biggest performance bottleneck in your entire computer. Okay, so to understand how engineers even begin to solve this problem, we first need to look at the basic ingredients they get to play with. It really all boils down to two main types of memory technology, and they sit on opposite ends of a classic engineering trade-off. On one side, you've got SRAM, or static RAM. This stuff is wicked fast. I mean, it's built using 6-hole transistors for every single bit of data it holds. But all that complexity makes it really expensive and kind of bulky, so you can't pack a lot of it into a small space. Then on the other side, you have DRAM, or dynamic RAM. It uses a way simpler design, just one tiny capacitor per bit. That makes it super cheap and lets you cram gigabytes and gigabytes of it onto a small stick. The catch? Yeah, it's much, much slower. So since we're mostly using that cheap but slow DRAM for our main computer memory, we really need to understand why it's slow. The delay isn't just random, it's actually a very structured, predictable process that's baked into how the memory is designed. So let's break down the timing of just one single request for data. You know, getting a single piece of data from DRAM is kind of like a multi-step dance. First, the CPU has to send the row address. Think of that as the street name. Then it sends the column address. That's the house number. Only after it has the full address can the memory start its internal work, which involves a built-in waiting period. After that delay, the data is finally read out. But wait, we're not done. The memory then needs a few recovery cycles to get ready for the very next request. Now, engineers have a specific name for part of this delay. It's called access time. This is what most people think of when they think of memory speed. It's just the time from when the memory gets the full address to when the data is ready. But as we just saw, that's not the whole story, is it? The metric that really matters, the one that tells the full story, is cycle time. This measures the entire operation, from the very beginning all the way through those final recovery cycles. This is the true speed limit. It doesn't matter how fast your access time is. You can't start a new request until one full cycle is totally complete. And that's what really determines how much data you can move per second. Okay, so we have this slow, multi-step process. The situation seems a little grim. But computer scientists are clever. They realized that programs usually don't ask for random bits of data scattered all over memory. No, they often ask for data that's sitting right next to each other. And so they designed some really smart protocols to take advantage of that behavior and start beating the bottleneck. Let's see how this plays out. Say you wanted to read 4 little pieces of data that are all neighbors in memory. The simple, naive way would be to just repeat that entire slow process 4 times. Send an address, wait, read, recover. Then do it all again, and again, and again. In a typical system, this could take around 7 clock cycles for each item. That's a total of 28 cycles. It's just terribly inefficient. But this is where the magic comes in. With a technique called burst mode, the CPU sends the first address, goes through that initial wait, and gets the first piece of data. But then, and this is the key, instead of starting all over, the memory just streams out the next 3 items one after another in the very next clock cycles. It assumes you want the whole block. And look at that. We just read the same 4 items in about 10 clock cycles instead of 28. That's a huge win. And this really shows you the impact in the real world. that simple change in protocol, just being smarter about how you ask for data, can take you from a memory bandwidth of about 1 gigabyte per second all the way up to 2.5. We're talking more than double the performance. But even that isn't quite enough to close that great speed gap. For that, we need an even bigger idea. So now let's talk about the most powerful and important strategy in all of memory design, caching. This is the brilliant trick that lets us have the low cost of that slow DRAM while getting performance that is tantalizingly close to that of the expensive SRAM. It's really about getting the best of both worlds. You see, the entire reason caching even works is because of one simple observation about how software runs. It's called the principle of locality, or sometimes you'll hear it called the 90-10 rule. What it means is that for any program, you spend about 90% of your time running the same 10% of the code over and over and over again. Think about loops or common functions. Caching is designed specifically to exploit this very human, very predictable fact. So how does it work? Well, a cache is just a small but incredibly fast bank of that expensive SRAM that sits right between the CPU and the main DRAM. Its only job is to be a high-speed buffer. It keeps a copy of that 10% of code and data, what we call the working set, that the CPU is using most often. So when the CPU needs something, it checks the superfast cache first. And the results are absolutely dramatic. Let's do some quick math. Let's say our slow DRAM takes 5 clock cycles to read, and our fast cache takes just 3. Now, if the data the CPU wants is in the cache 90% of the time, that's a 90% hit rate. The average time it takes to get data drops from 5 clocks all the way down to just 3.5. We've just cut the average delay the CPU has to deal with by a huge amount. And this, right here, this is the economic genius of it all. A system with only slow DRAM might cost, say, $200. A system with only that fast SRAM would be screaming fast, but it would also cost an insane $800. But the hybrid cache system, it costs just $300, way closer to the cheap option, but its performance at 3.5 clocks is incredibly close to the super expensive one. It is the ultimate win-win for cost and performance. Of course, modern processors take this idea and just run with it. They don't just have one cache. They have a whole hierarchy of them. There's a tiny, blazing fast level 1 cache right on the CPU core itself, then a slightly larger, slightly slower level 2 cache, and often an even bigger level 3 cache that's shared by all the cores on the chip. This whole multi-level system gets the average access time ridiculously close to that dream of 1 clock cycle per read. So we started with this massive speed gap. Then we saw how clever tricks like burst mode could chip away at the problem, and finally, how the magic of caching came in to give us the best of both worlds. But the fight is never over. We're creating more data than ever before, and we're starting to bump up against the fundamental limits of physics. So the question is, what comes next? What's going to be memory's next magic trick to keep those F1 race cars in our CPUs running at top speed? Thanks so much for joining me.